I don't classify those as our primary thing because those are it's not even that those are secondary. Usually with your oxidizing agents and reducing agents, they fall under one of those categories. Okay? All chemistry falls under one definition, which is the Lewis acid and base definition, except for radicals. Radicals are just a pain. But Lewis acids and bases cover everything because it's talking about the transfer of electrons from one source to another. If we subcategorize the Lewis definition down, we get nucleophiles and electrophiles, where we're looking at the transfer of electrons between, that might be the harder definition. We get the nucleophiles and electrophiles under Lewis acids and bases, and we get Bronsted-Lowry acids and bases under the other subcategory. What's a Bronsted-Lowry acid base? We're looking at electron transfer between protons. Nucleophile and electrophile? Anything that's not protons, because it's still looking at an electron transfer to a certain extent. In the Bronsted-Lowry, we're just looking at that electron transfer happening to or from a proton. Okay? So those are our big definitions. Being able to identify those in any given reaction is huge, because that starts to narrow our field of view from, oh my God, I've got all these reactions to memorize, to what does that central thing do? What does that central functional group do? What is the functional group in that now red box? I'll even accept two answers for this. Alkene. What would be the second answer I would accept? Alkane is our other functional group. Why do we not care about alkane? There you go. We don't get a lot of chemical reactions with our alkanes. Okay, so our alkene now gives us some chemical reactivity. So what we need to do is look at that structure and say, ah, there's an alkene. I have a pi bond. What does a pi bond do? What does a pi bond have? Electrons. What does the alkene act as? Nice dodge. An electron donor, which is a nucleophile. Which means, what do I need to find in all, well, actually we can push that a little bit further, a nucleophile, or what other species donates electrons? What other reagent class donates electrons? Bronsted bases. So let's take a look at all of the reagents that we've got around here. HBr is acid. What do acids react with? Bases. Oh, look at that. Br2 is, that one's a little bit harder. And electrophile, what was the alkene? Nucleophile. Br2? Electrophile, nucleophile. Electrophile, nucleophile. Mercury? Electrophile. What's the alkene do? Nucleophile. All of those reagents are following under those same basic classifications. Yes, you're responsible for knowing those reagents, but if you can pick up some of those classes, you can now start to weed out other things. For instance, would I add a base to an alkene? It doesn't really make sense to add a base to an alkene, because what does an alkene supply? What does a base supply? What happens when the electrons get near each other? They repel, we don't get anything happening. Okay? So looking at back to those basics and just applying those through, that can help you start to manipulate and figure out how does an individual reaction occur. Some of them are more quote-unquote obvious than others. Okay? Everything up there you should have already seen. That's all officially first semester stuff. Okay? Questions about any of that? Okay. So let's take a look at the addition reaction. We're taking an alkene, or really a pi bond, and we're trying to react it with something. So we've got an example of a reaction up above. Any idea what La and Lb stand for? Lewis acid and Lewis base. So our reagent is supplying both of those in this case. Okay? When we look at this, we may not see any reactivity. You look at the pi bond, is there any charge? No, no charge, which means no reaction, just like an alkane. So what we want to do is look a little bit further. And one of the things that we can do is we can either move to looking at our orbitals, our molecular orbital system, which I will fully admit is a challenge, or we can push this to our other favorite 4/9 letter word, which was already suggested, resonance. What can we move when we look at resonance? Electrons. Where do we have electrons? In all of our bonds. Which of those bonds are we allowed to move in resonance? The pi bond. So I can take those pi electrons and I can put them on one of the carbons of the double bond. Just as easily, I could take those pi electrons and I could move them to the other carbon. So I get two possible results out of this reaction. Not even reaction, out of our resonance. And what you might say is, oh, 2, that's already more than I started with. What a useless proposition. Okay, but if we look at our two possible products, what can we now start to do? First thing, what do you see? Charge. What do we need to do with charge? Neutralize it. We can now start to do some chemistry by targeting either the negative or the positive. One of the things that we have to be aware of is that since these are resonance structures, I don't really formally have a positive, I don't really formally have a negative. All I really have are electrons. Okay? And since I have electrons here, I can't bring more electrons in. Okay? So I don't officially have that positive. But that negative I can start to play around with a little bit, and that's where we got the nucleophilic, or the basic character of our alkenes. Which of those two structures is the more likely one to react? Red or blue? I did draw two different ones, didn't I? Yeah. Baby steps. Why should the red one be better?
Because that's where the electrons are in the, well, let's see.
Which do you want to look at, negative or positive? Either's fine. I will say I lean towards positive, being optimistic. Sorry, that was the sarcasm. Which do you guys want to look at, positive or negative? Okay, positive. Thank you. That makes me feel better. Okay, take a look at our positive. What makes that positive more stable?
The argument.
Electrons. So what we need to do is look where are there electrons around that positively charged atom. Well, we could immediately reference the bonds immediately around it, but when we look at the positive charge in both the red and the blue structure, they both have the exact same number of bonds, so that doesn't really help. So what do? Move one atom further away. And in the red structure, we go out to an R group. What is an R group? Anything other than hydrogen. What's the difference between hydrogen and anything other than hydrogen? More electrons. Where does my positive charge want to be? Closer to the more electrons. That means when I now try and predict something about the reactivity, I only need to look at the red structure. Okay. Which then pushes us to the next question. What do we want to react this with? Well, we said it's an electron source. What are the possible things I can react with electron sources? Electrophiles, because an electron source is also known as a nucleophile. So if I can find an electrophile, ding, reaction runs. What else reacts with electron sources? Keep going to Lewis. I'm going to have to break you of Lewis. You're right, Lewis acid does, but Lewis acid is too broad. Give me more narrow. A Bronsted-Lowry acid. It's still an acid. What does a Bronsted-Lowry acid supply? H+. What does our alkene supply? Electrons. There's the negative. There's our para. Okay? So when we're looking at these reactions, we can either activate that pi bond to react with some other species by adding an acid. Okay? So the acid is really just being added to force that structure into something else. We now have charge. Now it can do something cool. Okay? Or we could use a really strong electrophile. Why do we have to use a strong electrophile? Why not a weak electrophile? How charged is the alkene? Point to the charge in the alkene. Silence is a good answer on that one. Where is the charge in the alkene? There isn't charge. Can I use a weak electrophile with a weak nucleophile? No. So we have to use a stronger electrophile to force the alkene to react. Okay? That's ultimately chapter 12, and it kind of moves into 24 a little bit too. The last thing that we could do is we could force the pi bond to react by adding a radical. Radicals just mess with everything. Radicals can do whatever you want. They're magic. That's why I hate them. Magic sucks. There I go with that sarcasm again. I love magic. Okay, so let's take a look at reacting our alkenes or doing an addition reaction with acids. Focus on the reagents present, not our end result. So if we go through and take our alkene and we add a strong acid, okay, give me an example of a strong acid. Hydrochloric acid, good. It's always fun asking an open-ended question. You never know what you get, like resonance. I appreciate that. HCl. Okay. The most reactive thing present in this solution is going to be the HCl because HCl is a strong acid. What do strong acids by definition do? Dissociate into their ions. And we have H plus and Cl minus. What's a big tip-off that the strong acid is the thing we should be addressing first? It's charged. Okay? So, what do we need to stabilize that positive? Electrons. Where are their electrons? And the pi bonds. Are the pi bonds different? Nope. So who cares? Pick one. Put the hydrogen on the structure. Draw the result. You got 10 seconds. Seconds are up. How many of you drew this? Only one person? Well, only one person did it. They must be wrong. Where did this come from? Let's try it this way. What did you draw? Where do you want the positive charge? Left, right? Where are you putting it? Right side? Okay. Which carbon? Most right? Second most right?
Second most right.
What else? Is that it? That's the answer? Pi bond where? Far left. Everybody get that one? The other possibility was you put the positive charge on that very first carbon on the right. What's the problem with that? That's the less stable of our resonance structure with our alkene. Okay, so we wouldn't want to do that. What is the relationship between these two structures? Resonance, which ultimately means if you were asked to provide the answer to this simple reaction or this first step, you had to provide both. Otherwise, you were only half right. Okay? Resonance is something that's constantly happening. So what we do is we draw our result and we see what happens. I was kind of obnoxious and leading in that case because, of course, I drew the one that was the secondary resonance structure, not the primary one. But it still gets us to that idea. Okay? So when we go through and run our reaction, what we have to do is now look at that result. Look what things can happen. In this case, we form a carbocation. Are carbocations good? No. They're charged. We have to stabilize them. How do you stabilize a positive charge? With electrons. Where are their electrons? Give me a little bit further than resonance. Right idea. Where are the electrons? In the pi bonds. Can I move the pi bonds to stabilize that charge? Yes. I need to show that. That is something that is possible to occur. I am now looking at two structures that I have to propagate forwards. Both of them still have that positive charge, which means I have to now look external to the structure to see if there's something else out there. Is there something else out there that could stabilize that negative charge? Well, if we remember, we started with HBr, right? You guys are just going to accept that?
No.
We started with HCl, but we're going to switch to HBr. Because I forgot the next step actually I think brings in HBr. Okay. So what we now have to go through and do is with that positive, do I have anything to stabilize it? Well, I have bromide, so what should I do? Negative to positive. What happens? Hey, see, I was right. We had bromine. I now have that result. Is that product now stable? All right, the very first thing we started off with, that we said was incredibly reactive, that we wanted to get rid of, was the strong acid. Do you see any more strong acid? Nope. We fixed the problem. Okay, do we have any charges left in our structure? Nope. Fixed problem. We now have a final product. Now deciding which product is favored, we'll save that for last semester. No. Which product is favored? How would we decide?
Stability of the carbocation.
We could go based off the stability of the carbocation, which is then making an argument on thermodynamics. What we're looking at is the temperature of our reaction, thermodynamics versus kinetics. So we'd really have to evaluate a full-on energy diagram, which I have no problems drawing out again, but I'm pretty sure I removed that drawing from my slideshow. Okay. So to answer this question, we'd really be kind of left with those two possible answers. On deciding which one was favored, we'd have to look for some other clues. What other thing is in there? Do we have a lot of energy? Okay. Do we have a lot of heat? Or do we have no heat? So we'd be looking at the stability of our products or the stability of our intermediates. Okay, and deciding based off of our energy diagram, where does our reaction go? Okay. Our general format, we've got in the lower right-hand corner. We take our alkene, we react it with our acid. Our acid is typically bound as H, go figure, because it's a what type of acid, Matt? Dang it. Bronsted-Lowry. I'm trying. It's our Bronsted-Lowry acid. Almost always will be bound to our nucleophile in the case of our acid-activated alkene reactions, or addition reactions. Okay. We'll typically have a solvent. Why is the solvent in such a font color that you can barely see it? Rarely does the solvent do that much for us. It's either they're actually acting as a nucleophile or it's just kind of existing to help us out. You'll notice the dynamics of our product. Where does the nucleophile go? When we look at the product, where did the nucleophile attach?
The tertiary.
The most substituted carbon, and our hydrogen went to the least substituted, okay, in the general format. Okay? Questions? Addition reactions with radicals. So let's go ahead and take a crack at this. This will be fun. Same idea as the last one. Focus on the reagents present and not necessarily the end result. What you need to do is find the most reactive species in both cases. Okay? Come up with the result. Come up with a result. Okay? If you're lucky, you're done in 3 steps. If you're unlucky, it could go on for a very long time. Hint, hint, hint. Okay? See what you can come up with in the next couple minutes.